trees are connected. Connected means that from every vertex we can reach every vertex by traversing our graph. So it's not the case that we have some part of our graph that's completely disconnected, so with no edges, to some other part of the graph. So our trees need to be connected. They can't have things like this. They cannot have cycles. So in order to make this a tree, I should remove one of the edges. And there's many equivalent definitions of trees. So it's a connected graph in which there's a unique simple path between every pair of vertices, or alternatively, you could define it as a connected graph where there's one fewer edge than the number of vertices. The number of edges in a tree is n minus 1. Or it's a connected graph in which there are no cycles. I think this is the usual definition. And it can also be as a connected graph where whenever we remove an edge, we disconnect the graph. These definitions are all equivalent. How would you, for example, prove this property? Let's assume that we have a tree with no cycles, a connected graph with no cycles, and then we want to show that there's one fewer edge than the number of vertices. We can do it by induction. So this is a connected graph with one vertex and no cycles. There's one vertex and 0 edges. So the property holds for this simple graph. Now, by induction, we could take our tree, our large tree, assume the property holds for all the smaller trees. Remove one of the leaves, any one of the leaves. Removing it deletes one vertex and one edge. And by induction, the property is true for the smaller tree. And since it's true for the smaller tree and for the larger tree, we have one additional vertex and one additional edge. And it's also true for the larger tree. So basically by induction, by starting from our base case and bootstrapping this kind of proof to larger and larger trees. We have proved it for all trees. Okay, and as usual at the end of the lecture we have a puzzle. This time we're not going through any hints. Let's quickly run through what it says. So we have a circular highway. We have n petrol stations, unevenly spaced, so there's no regularity to these petrol stations. Each contain a different quantity of petrol. And what we know is that, well, the quantity of petrol on all stations taken together is enough for our car to go around the highway once. Your tank is unlimited size, so it's basically it can fit as much petrol to go around the whole highway. What we need to do is prove that there always exists a station among all of the stations, such that, well, if you take that station as a starting point, you start from an empty fuel tank, well, fill up at that starting station. You can basically go around the highway without ever running out of petrol. There's a nice proof by induction that you can do. You can try out. But
we're not going to show it.
That's it for the preliminaries lecture. So I think I'll jump right into the divide and conquer lecture before taking a break, unless you have questions. Okay, so what is divide and conquer? We have already seen some examples, right? Merge sort is a type of divide and conquer algorithm. So in this lecture, we are going to view these kinds of algorithms more generally and make more general statements about their running times. And we'll start with a coin puzzle. So we're given 27 coins of the same denomination. We know that exactly one of these coins is counterfeit, and this particular coin is lighter than all the others. So all the coins have the same weight, just one of them is a fake coin and it has lower weight. So find the counterfeit coin by weighing coins on a pan balance only 3 times. What's a pan balance? So it's a
left hand side, right hand side.
Thing like this, where you have a plate here and a plate here. You
$27 coins. So if it's 27 coins, it's 27 divided. Let's just do a typical thing that you do. It's 27 divided by 2. 14, 13. So 14 here, 13 here. So if this one's heavier, whatever, this one's... Oh, true. That's not good because we don't know the weight of one. We could do 13 and 13, I guess. And then we'll just have like a 1 chilling here. Six and a 6 if they are the same weight. then it has to be 1. Same logic here. So we got 1, 2, 3. Oh, this is not good. Because if I do that, I can't do it in the right amount of turns. We find out this side is heavier. Then we have one more way in. That one more way in, we have to somehow Okay, how about we try to make it a branching factor of 3? Because if it is in the case, then it might help out. Wow, it's the exact same. Yeah, I could tell by the number 27 it wanted a branching factor of 3. And then with those, we just go. Nice.
Put your items on the 2 plates, and then you can see whether they have equal weight or one of them has larger weight than the other. So there's 3 outcomes. Halves, and then combine them. And sorting the 2 halves is done recursively. Right? So these recursive steps are kind of a feature of our divide and conquer algorithms. We'll now look at counting inversions in an array in movies, and you want to determine for any 2 users, A and B, that we'll now look at counting inversions in an array. So, okay, so what is this? So let's say that we have n users ranking the same set of n movies, and you want to determine for any 2 users, A and B, how similar their tastes are. And so there's a question, well, if you have 2 rankings of all the movies, how can you determine how similar 2 rankings are? And one way of doing it is to count the number of inversions. So you can list all the movies of user B in order, so from their most preferred to their least preferred. and then look at how user A ranked the movies. So let's look at the example. So for user B, we rank the movies. So the first movie is movie number 1, second movie is movie number 2, etc. And now for each of these movies in order, we look at what place did user A rank that movie. So basically user A said, well, for the first movie, for the highest ranked movie of user B, I agree this is the highest ranked movie. For the second ranked movie of user B, user A says, well, this is actually 5th in my ranking. So etc. So we have two lists, one for user B and one for user A. Without loss of generality, we can assume that user B's items are ranked from 1 to 12, named from 1 to 12 in the order that user B ranks them. And now we have the ranking of these movies for user A. And now, well, basically we want to give a penalty whenever user A ranks 2 movies in a different order than user B. And we say that this is an inversion. For example, let's say movie 2 and 7. Well, they form an inversion because B ranks 2 earlier than 7, but A ranks 7 earlier than 2. Now we want to count how many inversions are there in the lists. So to access the rank of user A's 9th ranked movie of user B, we take A of 9 equals 3. So a good measure of how different the two users are is the number of pairs of movies which are out of order between the two lists. So that's exactly the number of inversions. And then an inversion is a pair such that, well, B prefers I to J and A prefers J to I. So we want to count the number of inversions. Okay. Try and start thinking about an algorithm to do this, to count the number of inversions, and to use our divide and conquer method. Maybe another example here. For movies 1 and 7, there's no inversion because, well, they occur in the same order in both lists. For movies 2 and 4, there is an inversion because they're out of order. So counting number of inversions can, well, the easy algorithm would have running time order n squared, or even theta n squared. But this is because, well, you can look at all pairs of movies. Going through all pairs of movies is already order n squared time. And then, well, we see whether they occur differently in both lists. They occur in different order in both lists. So the running time of such an algorithm would be order n squared. We want to do something faster. So we aim for a running time of order n log n. Okay, so we have to divide our instance into, let's say, 2 parts. Let's try 2 parts, maybe 3 parts. And we cannot count the inversions one by one because just there's order n squared pairs, right?
That's pretty fun.
Christian conservatives have had.
Oops.
So we need to do something smarter. So our algorithm will have similarities with the merge sort algorithm. So we're going to try to split our array into two. And then, so what do we need to count actually? So we take our array, split it into two halves, and okay, so maybe there's some. So the two halves are called AL and AR. Okay, so we can probably recursively compute the number of inversions inside AL, compute the number of inversions inside AR, but then there's some inversions that go across, right? So there's a question of, I think that's the main challenge, is how to count the inversions that go across the two halves. So let's do a 10-minute break and while you think about the solution, and then we'll resume in 10 minutes. Okay.
Count the number of inversions. There has to be a leak code question on that. Is that the coin problem? This is the exact same question. Zero equal to zero is less than or equal to I equal to J. Return it modulo. Sure. What? Huh? Given two integers n and k, return the number of different arrays. Different arrays consist of numbers from 1 to n, such that there are exactly k inverse pairs. Huh? Bro, what the frick? This is crazy. Screen didn't even get bigger.
How to of inversions is the inversion. Okay, let's continue. I think sorting the, or not sorting, counting the inversions inside and L and A of R is quite easy if we continue our divide and conquer approach. Counting the number of inversions across seems challenging. So that's the main challenge. So the total number of inversions is the inversions inside of AL, inside of AR, and across, right? So first two are easy. The main challenge is to evaluate the last term. So one question is, for this example, how many inversions involve the 8? Well, it's of course all the inversions inside of AR that involve the 8, which is just one inversion between 8 and 2. And then all the inversions that go across. And which inversions go across? Well, it's as compared to the 8, well, if some numbers that are larger than 8 occur in AL, then they form inversions with 8. But still, it's not obvious how to count the number of integers on the left that are greater than 8, right? If somebody gave us a sorted version of AL, it would be easier. So how do we do this? So we're actually going to do two things. We count the inversions on the left and on the right, And we also come up with a sort of both sides. So we're going to sort both sides. Maybe keep the sorted version in a different way, because we still need to count the number of inversions inside, right? Okay, so if we actually have a sorted version of the left and the right, now we can count the number of inversions across quite easily. So what are we going to do? So we're going through AR one by one. Okay, so we encounter this 2 here. We want to look at, well, how many elements in AL are smaller than 2. So that's just this one. And we can find it, well, towards the beginning of AL, and we'll actually walk through AL one by one. So the first element is smaller than 2. So that gives us a count of 1. Okay. Now we have our 2 that we put into our final list. What's the number of inversions? Oh, wait, okay. Okay, I misspoke earlier, sorry. Let's start from the beginning.
What?
So we're going through AR one by one. So we have this number 2 that we encounter. It doesn't form an inversion with 1. We put 1 in our sorted list. It does form an inversion with the next number, 5. Okay, so from that moment onward, we know that it forms an inversion with all the remaining elements of AL. And well, we know the size of AL, we know how many values we have already copied, we can keep track of this. So we know that, well, 2 now forms 5 inversions with AL.
What?
So we put 2 into our sorted list, and then we count 5. Okay, then we have handled, well, this 1 and the 2. So we go to our next item in AR, that's 3. So it's smaller than the next value in AL, so we put it into our sorted list. It forms an inversion with, well, everything that remains in AL, which is these 5 numbers. So we increase our count by 5. We look at the next item in AR, which is 4. It's smaller than the next item in AL. We put it into our sorted list, and so the number of inversions is still 5. So we add that. So now, when we look at 6, we detect, well, 5, the next element in AL is smaller. So 5 goes into our sorted list. Then we have 6, that's now smaller than the next item in AL. And we know that AL contains 4 elements that we haven't seen yet. 6 is smaller than these 4, so we increase our count by 4. And we can keep doing this. So by doing this, we do 2 things. We create a sorted version of our list, and we also compute the number of inversions, which happens to be 23, and that's the number of inversions across the 2 lists. Okay, so basically by doing 2 things at once, like sorting and counting inversions, we have now, well, divided our array into 2, and when computing number of inversions, let's say we have handled the smaller lists, which means that we have the number of inversions in the smaller lists. We already have a sorted version of the smaller lists. So we have done all of that. Now, to sort our bigger list and to count the number of inversions that go across. We already have computed the ones that are inside A of L and A of R. To compute those that go across. What we did is, well, we stepped through AR one by one. We kept the index of AL where we are currently at. So we stepped through both AR and AL, like in merge sort. We process the elements in the very same way as merge sort. So the running time will actually be exactly the same as the running time for merge sort. Okay. So we have done everything we need to do for the AL and AR recursively, and now we just need to count the inversions that go across. This adding up these three numbers gives us the total number of inversions. Okay. Maybe since today we're going to see more generally how to analyze the running time of divide and conquer algorithms. So let's maybe let's recall why the running time of merge sort is order n log n. So what do? We start from a list of size n. And then we create two lists of size n half. So the size decreases by factor 2. And the number of instances we have at the first level is we just have one instance, then we have two instances at the second level. We keep dividing the size into 2 and multiplying our number of instances that we're solving by 2. Right? So here we have instances of size n divided by 4, and we have 4 of them. This goes on until we have tiny instances of size 1. So at some point the size becomes 1, the number of instances becomes n. So what's our computation time that we need at each level that we have here? So let's look at this level, for example. And so when handling, well, this instance in this level, it's basically the number of so the amount of computation that we need is, well, basically merging these two lists, or these two arrays, and, well, in this case also keeping track of the number of inversions. But I guess the running time that we need is order the size of this list, and how many things are we. we're handling, well, let's order the number of things that we are handling. Okay, but we can see that, well, when multiplying these two things, we get n, right? At each level. At each level, we do n computations, or order n computations. So if we multiply these two things,
Then we get the,
the size and the count, we get n at each level. So how many levels are there? How many? Log n? Yep, yeah, that's correct. So we have log n levels because, well, we can see that basically level I has size n divided by 2 to the power I. So we have n divided by 2 to the power 0 up here. 2 to the power 0 is 1. We have n divided by 2 to the power 1, n divided by 2 to the power 2, etc. And we can only divide by 2 log n times. Log base 2 n times. Yeah. Okay. So basically the number of values of n I've written here is order log n. And that's where the running time comes from. We have n times n log n. N times log n. Okay. So we're going to think about these recurrences more generally. So for merge sort, we had that, well, to solve something of size n, we work it up into two, and two things of size n half. So we created two instances of size half. We need some time to solve those. And then, well, to merge the results, it took us some time, right? So it took us order n time. So now, basically, well, we're going to see the master theorem, which allows us to, well, based on this value, and this value, it gives us the final running time. So for recurrences like this in general. Instead of 2, we could have any number. Instead of that 2, we could have any other number. And this could be any function in n. Right? Or I guess the master theorem applies to certain common values for these. Okay. So basically, this is what we had. If I'm not happy with the big O of n, we can replace it by c times n. Okay, so now we have some integer a and some real number b. So basically, the integer a is the number of sub-instances that we create, the number of instances we break our large instance into, and b is basically the factor by which the size reduces. So So we'll have A subproblems of size at most n divided by b. So basically, if we go back, so this will now be an A, this will be a B. And now we can still have some flexibility to change this. Okay, and so this function is, so this function that we use to merge the arrays, or to basically split the problem into subproblems and then combine the solutions from the subproblems into the solution for our big problem, takes time f of n. Okay, so that's our recurrence now in general, our generic recurrence. And, well, we need to find out, well, if we have such a recurrence, what's the running time that this gives us? It cannot be always n log n. This function f of n could be huge, it could be n cubed, so then we would need time at least n cubed. We will disregard floors and ceilings. Everything is behaves nicely when ignoring them. Okay, so what is this? This is basically our recursion tree. We start from our big instance. Every time we make a recursive call, we have an arrow to our sub. Instance. So basically, this big tree models the recursive calls of our algorithm. So from our original instance, we create A subinstances. From each of those, we again create A subinstances, etc. And when creating a subinstance, we divide the size by B. Okay, so what do we have here? So this is our recurrence, remember? We start from an instance of size n. Then we create A many subinstances of size n divided by b. And I guess, so these are the sizes of the subinstances. The depth of the recursion is log base b of n.
I guess they use the letter b.
Let's also count the number of instances at each level. Level. So we have one instance at the top level, then we have A instances at this level. We have
I didn't really get the counting algorithms one. Could come back to it later. I don't get it. Are these not usually the same? Or measure the same? Are these both the branching factors? I thought they're the same thing. Oh, the slides suck. PDF would be better. No file. size of instances equals n divided by b squared. I don't get how A and B aren't linked.
I guess. So every time we go one level down, the number of instances multiplies by a, right? So a squared instances here, dot dot dot, until we have, I guess, n instances down there. Now n instances in the worst case. It could be that the numbers are not nice, and so that some levels stop earlier, but at most end at the last level. Okay. So now we can. So basically, the master theorem will have three cases. Actually, let's get back to this picture later.
Bro, this guy doesn't explain
so
anything.
we want to solve these recurrences. For some of them, you can solve them explicitly. It's not so easy for these ones. And so that's why we rely on this master theorem that it informs us about the running time. So let's look at the statement of the master theorem first. So again, a is this integer, b is a real number, greater than 1. Yeah, so b needs to be greater than 1 because, well, we need to make some progress, so we have to make our instances smaller. If they become larger, then it's hopeless to solve the problem. F of n is a non-decreasing function defined on positive integers. I guess all our instance sizes have sizes that are integers. And T of n is a solution to this recurrence. Okay, now there's something called the critical exponent, which is log b of a. And the critical polynomial n to the power c star. And then, depending on how this compares to f of n, we get one of three cases in our running time.
Bro,
But
what is he talking
let's go back to the previous picture and see where this critical exponent comes from. Okay. Let's think about the size of this tree. Well, we have something about the sizes of the instances. We have something about the number of nodes at each level. So what's the total size of this tree? And we know the recursion depth. So what's the total size of the tree? Well, it would be 1 plus a squared plus etc. I guess most of the nodes would be at the very bottom level, right? So there's n nodes at the bottom level. Okay. So as in quicksort, we'll also be thinking about, well, the sizes at each level. Okay, I guess I was lying earlier. I said there's n nodes on the bottom level. That may not be true. because, well, we're creating A subinstances, all of them have size n divided by b. It could be the case that, well, A is huge, but B is tiny, or B is close to 1. So we actually, our trees will become much broader than this. So this is not good. Okay. So how many nodes are there actually on the last level? Well, let's see. At each step here, when we go one level down, we multiply the number of nodes by A. So here we have a to the power 0, here we have a to the power 1, a to the power 2, etc. And we know something about the depth of our recursion tree. So we know it's log b of n. So at the bottom level, we might actually have up to a to the power log b of n many nodes. Okay. One thing about these rooted trees and is that I guess our trees are, so A is at least, let's say A is at least 2. Actually, is that one of the conditions or not? A could be 1. What if A is 1? Okay, A is 1 is a special case, because, well, we're just creating this very linear tree, and B decreases each time. Let's assume A is at least 2. Then actually most of our nodes will occur on the bottom level. And the total number of nodes, let's assume that this is a full tree, so we, basically it's a complete tree where the bottom row is full. Most of the nodes will be on the bottom level, and the bottom level will actually contain more nodes than occur in the rest of the tree. Here's one extreme example, if there's at least 2, is binary trees, where the number of internal nodes is 1 less than the number of leaves, if you have a full, complete binary tree. Okay, so we mostly care about the number of nodes on the bottom level, and then we can upper bound the number of nodes in the whole tree by twice this. So it will be, we have order A log B of n nodes in the tree. A to the power log bn is not a nice function. We really want polynomial function, right? Is this a polynomial? Yes? Okay, don't give the solution back. Yes, correct. So let's try. So there was one suggestion that, well, we can swap the a and the n. Why is that case? Let's try to work through it. A to the power log b of n. We want to do it, let's say we want to make a change of base for the log. We actually are happier with the log base a, because we have a in the base. Log base a of n, and then we have to divide by log base a of b. Okay, now we can say that this is equal to n to the power 1 divided by log base a of b. And now let's make another change of base. Let's go back to base b, actually. We get log base b of b, and then we divide this by log base b of a. Log base b of b is 1. So this will be n to the power log base b of a. And if you look at what we had before, we effectively switched a and n, right? So now we have this. So our recursion tree has order of n to the power log b of a many nodes. And this is exactly our critical polynomial. So C star is log b of a. N to the power log b of a was the size of our tree. So n to the power C star is our critical polynomial that corresponds to the size of the tree, of the recursion tree. Out to constant factors. Okay. So that's where this critical exponent comes from. And now there's 3 cases in the master theorem. So either, so we had the recursion was a times t of n divided by b plus f of n. Okay. So either this f of n is smaller by some epsilon in the exponent here, than the size of the tree, in which case, actually, the size of the tree is what dominates the running time. So in that case, the running time will be just order of n to the power c star, which is our critical polynomial. And basically, this computation here gets absorbed because it's no more than the size of the tree. There's one intermediate case which actually corresponds to merge sort, for example. So now here f of n is equal to theta of n to the power c star. So f of n is so it's a constant factor times the size of the tree. Then we have this additional log n term in the running time as a multiplicative factor. And the third case is that f of n is more than the size of the tree. So it's big omega of n to the power c star plus epsilon for some positive epsilon. And in that case, actually what dominates the running time is, well, this function here. There's one condition that needs to hold. So it needs to be true that for some c smaller than 1, and starting from some instance size onwards, n 0, we have that a times f of n divided by b is at most c times f of n. So basically, if you think of what happens in the tree, so at the top level, we need time f of n. And then basically to solve everything at the next level, where we have a instances of size n divided by b, so solving everything at the next level must take time that's smaller by a constant factor. So it's less. So the c here is smaller than 1. So some constant factor smaller than 1 times f of n. So basically, the computation at the next level must take less time than the computation at the previous level, asymptotically. So for large n. Okay. So these are the three cases of the master theorem. So we either have that, well, the running time is dominated by the size of the tree, or the running time, in case f of n is equal to more or less to the size of the tree, there's this additional, or this multiplicative log n factor. And if f of n is large, and basically the top level is what dominates the running time, then that's our running time. I guess there's something missing here. Okay, yeah. So so the running time will be theta of f of n. There's a little exercise here, which is proof that f of n is equal to big omega of n to the power c star plus epsilon is a consequence of this condition here. Okay, now if none of these three cases were true, so if none of these three cases hold, then the master theorem does not apply. How could none of these hold? We have that f of n is smaller than the critical polynomial, equal to the critical polynomial, or at least as much as something a little bit more than the critical polynomial. But there's a little bit more. Could, instead of increasing the degree of the polynomial here, it could be a log n factor or something. So it doesn't always apply, but it's quite general. And well, when it doesn't really apply, we can still tweak it often to still make it work. So one example is when we have that 2 times t of n half plus n log n. So what's the critical exponent? So c star is log base 2 of 2, which is 1. So now we need to compare f of n, which is n log n, and n to the power, well, 1 plus epsilon, or n to the power 1 minus epsilon. And
what are they talking about?
So is it bigger of this? No. Is it theta of n? No. Is it big omega of n plus n to the power 1 plus epsilon for positive epsilon? No. Well, it's kind of, it grows quicker than n, but it doesn't grow as quick as n to the power 1 plus something, right? So n log n somehow sits in between these two. Okay. So there's a remark here that the base of our logarithms are not important because they just mean constant factors in our 1 in times that disappear when talking about big O, big theta, or big omega notations. So we can ignore the base of the logarithms. However, this is not the case when the logarithm occurs in the exponent, where in the exponent constant factors are important. N to the power 2 is not the same as n to the power 3, right? So in the exponent here, the base of the logarithms, they matter. Yeah. Okay, let's go through a few examples. So the first recurrence is t of n equals 4 times t of n half plus n. That's basically like doing merge sort, but then each time creating another instance of merge sort. So the critical exponent c star is log base b of a, so log base 2 of 4. So it's 2. So the critical polynomial is n squared. And basically what this tells us is that, well, what matters here here is the size of the recursion tree. This thing is negligible. So the running time will be order. Okay, so first of all, this f of n is order 2 to the power n to the power 2 minus some epsilon. So there exists a positive epsilon where the running time is this. You could take epsilon equals 1, or you could take it between 0 and 1, for example, 0.1.
What was epsilon?
So this satisfies the condition for case 1 of the master theorem. So the running time will be big theta of n squared. Example 2 looks very similar to merge sort, right? So we have the critical exponent is 1, log base b of a, so log base 2 of 2 is 1. So the critical polynomial is n. And so this corresponds to case 2. So of course 5n is order n, it's big theta of n. Sorry. So this corresponds to condition case 2 for the master theorem. So the running time will be big theta of n to the power of the critical exponent times log n. Okay, the third example is t of n equals 3 times t of n divided by 4 plus n. What's the critical exponent? It's again log base b of a. It's more or less, so we can see that it's less than 1, because log base 4 of 4 would be equal to 1, so this is less. It's about 0.79. The critical polynomial is n to the power log base 4 of 3. And so now we compare the critical polynomial against n. N goes faster. And we can add an epsilon into the exponent here. So we have f of n is equal to big omega of this function. Moreover, so there was the second condition that a times f of n divided by b should be at less than c, for some c smaller than 1, times f of n. So a times f of n divided by b is 3 times f of n divided by 4.
What is going
and this
on?
is so this is f of n. So this is equal to 3/4 n. This is indeed less than c times n for some c smaller than 1. You can take c, for example, anything between 0.75 and 1 would work, right? And take it to be 0.9. Okay, so together this satisfies case 3 of the master theorem. So the running time is basically theta of f of n. So this is the case where basically at the top instance, whatever time is spent by splitting and merging, or splitting and combining the solutions, takes most time in total. Okay, and then we have a case where we can compute a critical exponent, but here we have this n log n term, which doesn't really fit the master theorem. So none of the conditions apply. So we can't really apply the master theorem. So here's an exercise. Prove. Is this clickable? No. Prove the statement here. That no matter how small we choose this epsilon, n log n will not be big omega of n plus n to the power 1 plus epsilon. In other words, prove that for every epsilon greater than 0, every constant c greater than 0, that occurs here, and every integer n greater than 0, there's some integer greater than n, so such that log base 2 of n is smaller than c times n to the power epsilon, which is exactly what you need to prove to show that to show number 2. You just plug in the definition of the big omega and then negate it. Okay, one hint is to use L'Hopital's rule to show that log base 2 of n divided by n to the power epsilon tends to 0 when we increase n. So L'Hopital's rule says you can do this by taking the derivatives both on the top and on the bottom. Okay, so that's left as an exercise. So let's start to unravel the master theorem. So the master theorem says that, well, these are the recurrences we deal with, a times t of n minus b plus f of n. So if we replace this term, t of n divided by b, basically and plug in the definition of t, we can make one step of the unraveling. So what is t of n divided by b? Well, it's, again, a times t of, well, this thing divided by b. So it's n divided by b squared, plus f of this thing, which is n divided by b. And now we can plug this in. And then we get that t of n is a times whatever we had here, plus f of n. So if we multiply everything in here by a, we get a squared times t of n divided by b squared plus a times f of n divided by b plus f of n. So basically here we have the computation that occurs at the first level in our recursion tree. Here we're dealing with a instances, each of size n divided by b. So this is the amount of computation that goes on at the second level. And then this expresses what goes on below. And we could make another step of unraveling. So this is what we have. So let's do another step of unraveling. So we replace this by the definition of t, and then plug it in. So now here we get the amount of computation that occurs at the third level of the recursion tree. And we can keep going. And we see this pattern emerging. So we have this a to the power something, f of n divided by b to the power something, right? So if you keep going, so we will find that, well, doing this k minus 1 times, we'll get terms that look like a to the power I times f of n to the power, n divided by b power I. And then we still have something that's undeveloped. So how many times can we do this? How many times can we unravel? Well, when actually the level that we are looking at becomes deep enough, then at some point we'll get instances of size 1. So when does this happen? Well, it's actually when k is, as we saw in one of the earlier slides, is like log b of n. So basically we can do this. So we can at some point go from I equals 0 to log b of n. Okay, so what do we have here? Here we have that n divided by b to the power k for this value of k gives us instances of size 1. So basically, these can be handled in constant time. And we have this term that remains, and we saw it earlier when we looked at the big tree, and we looked at the number of leaves in this tree. That was exactly a to the power log b of n. And then we saw that we can swap the a and the n, and so this is equal to n to the power log b of a. So our t of n is equal to n to the power log b of a times something constant plus this sum here. Oh, and we haven't replaced the function f yet. We haven't assumed anything about it. Okay. So now in order to prove the master theorem, we'll be working with this expression, and the first case that we're looking at is case 2.
Bro, what?
Here we have f of n is big theta of n to the power log b of a. Then we can look at the sum. And so this is the sum again. So we replace f of n divided by b to the power I by this expression. Basically, that just means that we replace the n by n divided by b to the power I. That's all we did here. And now we can take the theta out and say that, well, all of this is big theta of this, and we didn't change anything else. That's by the properties that we saw about the big theta notation and the big O and big omega. Okay, so now we've written our sum like this. Okay, so this n to the power log b of a occurs everywhere, and it doesn't depend on I, so I can just take it out of the sum and put it in front. And then this n here gets replaced by 1. And what's the next step? Now we can say, okay, so we take, okay, a to the power I. Okay, we have to stop very soon. Okay, I put a to the power I on the top of the fraction, and then b to the power log b of a goes on the bottom, and I take the I that was here outside of the fraction. That's all that's going on. And we'll be stopping here and continue on slide 43 on Thursday. Okay, thank you.
Bro, what? This guy's explaining nothing. Not looking good for your blood. Is this not case 1? Oh no, okay. Nice. What? What? Did I just infinite glitch it? No, I didn't. I didn't. I'll go here. You can block like that, then I'll take. Or you could go there. And then I'll take the pawn, I guess. Lay. Just need one more hit. Could take the pawn for free. What do I do here? Huh? I don't get it. Whatever.
Analyzing this type of recurrences, and we saw that the master theorem is helpful for this. Okay, let's recall this slide. So remember that this is the recurrences that we care about. So initially we have an instance of size n. We create a instances at this level of each of size n divided by b. So we have a such instances, each of this size. And then at the next level, the number of instances multiplies by a. So we have a squared instances, each of size n divided by b squared. Okay, and then we can continue this, this reasoning and find out that, well, at the lowest level, we have instances of size 1. Each of them has size a to the power the recursion depth, which is log b of n. So we have instances. We have this many instances of this size, right? Okay, and we figured out that, well, the number of instances at the lowest level corresponds more or less to the size of this whole recursion tree, because well, the number of nodes in total can be upper bounded by big theta of the number of nodes at the lowest level. And this can also be rewritten as n to the power log b of a. So we found that, well, this polynomial high is really important, and it's called the critical polynomial in the master theorem. And log b of a is the critical exponent. And so the master theorem has three cases. One of them is that the whole running time is dominated by just the size of this recursion tree. And I guess the other extreme case is that the whole computation is dominated by whatever is computed at the first level. So these are two of the cases. And I guess there's one special case where the running time on the first level corresponds exactly to the size of the recursion tree. In which case, well, it's this critical point where actually both of these factors contribute. And the running time will be this times some logarithmic factor. Okay. So let's recall the statement of the master theorem. We have this critical exponent here, and the critical polynomial, which is n to the power of this exponent. So the first case is that when the computation at each level is smallish, so it's less than the size of the recurrence tree, and so we can actually remove an epsilon from this exponent here. So then running time is dominated by just the size of the recursion tree. If the running time needed for the combination step is equal to the size of the recursion tree, then we have this multiplicative log n factor in our running time. And if the running time is large, and we have this second condition, that basically says that, well, the running time at the upper level, let's call this the first level, is big omega of this. And when we go down the level, we create a instances, each of size, n divided by n divided by b. So if the computation time at the second level is less than the computation time at the first level by a factor c that's smaller than 1, then actually whatever happens at the top level is what dominates the running time. And in that case, the total running time is big theta of f of n. Okay. And if none of these conditions hold, is epsilon. So let's recall the statement of the master theorem. We have this critical exponent here, and the critical polynomial, which is n to the power of this exponent. So the first case is that when the computation at each level is smallish, so it's less than the size of the recurrence tree, and so we can actually remove an epsilon from this exponent here. So then running time is dominated by just the size of the recursion tree. If the running time needed for the combination step is equal to the size of the recursion tree, then we have this multiplicative log n factor in our running time. And if the running time is large, and we have this second condition, that basically says that, well, the running time at the upper level, let's call this the first level, is big omega of this. And when we go down the level, we create A instances, each of size, n divided n divided by b. So if the computation time at the second level is less than the computation time at the first level by a factor c that's smaller than 1, then actually whatever happens at the top level is what dominates the running time. And in that case, the total running time is big theta of f of n. Okay. And if none of these conditions hold, then the master theorem is not applicable. But sometimes you can still take the same reasoning as in the proof of the master theorem and make it still worse. Okay. So let's we went through some of the examples. Let's scroll forward a bit. So we started to unravel this recurrence in the master theorem. So this is the recurrence that we are starting with. Now we replace t of n divided by t of n divided by b by its definition. So t of n divided by b is this. We make the replacement, and then we obtain this new recurrence down here. So we have a squared of a squared times t of n divided by b squared, plus basically the computation time at the second level of the tree, plus the computation time at the first level of the tree. And then we can do this one more time. Now we have determined the computation time at the third level of the tree, and then everything below that is still hidden in the first term over here. And by continuing this reasoning and by figuring out, well, what's the depth of our recursion tree, we can finally get to this point. So at the final level of recursion, our instances have size 1. We have this many nodes at this bottom level, and this basically models what happens at level I of the recursion tree. Okay. So on Tuesday, we started to look at what happens in case 2 of the master theorem, which is the simplest case. So in this case, we have that f of n, so this running time that we need for combining the solutions, is big theta of the critical polynomial. And so we'll be plugging this into here. So what happens now? So this is the sum that models what happens at all of these levels I of our recursion tree. So at the top level, we have a to the power 0 of f of n. So we just have f of n. At the next level, we have a times f of n divided by b, etc. Okay. And what we started to do was now replace this f by the definition that we just get from looking at the second case of the master theorem. Now we're able to take the big theta out by just the properties that we saw when discussing asymptotic notations. That's all that happened at this point. And now what we're doing is, well, we're looking at this n to the power log b of a. This term is completely independent of I, right? So we can actually take it outside of the sum. And then in the next line, we are putting a into this parenthesis. We're replacing, we're taking this exponent inside the parenthesis and I outside, actually.
Bro, he's not explaining.
I guess if we would add another step, we would say,
I can see that.
Okay, so this is 1 divided by b to the power I times log b of a. Now take the log b of a inside the parenthesis, and then take the a to the power I and put it inside. Okay? And then we get this expression. Okay. So that's where we are. B to the power log b of a is just a, just by definition of the log. So we get a divided by a, which is 1. And, okay, so which means that all we're going to do is multiply this number by log b of n minus 1. I guess we can forget about the minus 1. It's not a dominant term. Okay. And I think we're pretty close to where we need to get, because what we need to show is that running time is, well, the critical polynomial times a logarithmic factor, times log of n. And, well, as usual, for the logarithmic factors that are not in the exponent, right, we can just forget about the base because those just modify our running time by constant factor, which is basically irrelevant when we look at the asymptotic notations. Okay, and so this completes the proof of the second case of the master theorem. Feel free to ask questions if things aren't clear. If we now look at the first case of the master theorem, we will see that while the proof is very similar, except that where we had the sum of ones over here, we're actually going to get a sum of b to the power epsilon times I. Okay, so and for this sum, we'll use a result about geometric series, which says that, well, the sum over r to the power I, when I goes from 0 to, I guess, k minus 1, is equal to r to the power k minus 1, sorry, minus 1 divided by r minus 1. Okay, so I guess we can do some pattern matching here to now replace r by b to the power epsilon. And then we should get b to the power epsilon minus 1 divided by, well, there's a k here, okay. But let's check how far our sum goes. So our sum goes up to the critical exponent minus 1. So we would have something like log b of a, and then b to the power epsilon minus 1. Okay. Then making this replacement, you can prove case 1 in a very similar way. Now, in case 3, we have this additional condition. Here we have that T of n is big theta of f of n. We have this condition that T of n okay.
Case 3
We're going
looks
to use this
like
condition
this.
later. Okay. So case 3, let's recall the master theorem. So in case 3, we need to prove two things, because we need to prove this, which can be decomposed into two separate proofs. One is to show that T of n is big O of f of n, and the other one that T of n is big omega of f of n. Okay, so the first thing is to prove that T of n is big omega of f of n. We can just use so this statement. T of n is equal to a times T of n divided by b plus f of n, which is our recurrence. So we can see that here that T of n must be kind of at least as large as f of n, because f of n is one of the summands, right? So even if this thing here was 0, then T of n would still be at least f of n. So the first part is obvious. For the second part, we need to show that T of n is big O of f of n. So basically, and it means that so actually everything is dominated. The whole computation time is dominated by the computation time at the very first level. At the very first level, to just do the merge step or the combination step, we need f of n time. And now we're going to prove that, well, this actually dominates the whole running time. Actually, you're going to prove it because it's an exercise. Okay, so to do this, you will need to take the sum and upper bound it by f of n, by some constant times f of n. And here you need to use the equality, which is the additional condition in the master theorem in case of 3, and basically bound it at all the levels of this recursion tree. So when I first saw the master theorem, it was quite strange because, well, why would the running time behave like this? But I guess thinking about this big recursion tree and seeing what amount of computation is done at each level, it's kind of natural to figure out what happens. So let's try to apply it to a few problems. And the first one is integer multiplication. So what is integer multiplication? Well, we will need to multiply two integers together. So the first thing here is, well, before we multiply, we need to know how to add. So actually, we'll be thinking about our input now as two integers, each with n digits. right? So we have here an integer with n digits, and then another one with n digits, and we want to add them together. And we assume that, well, thinking about two single digits, or making some elementary operations on two single digits takes constant time. So if we take two digits, add them up, we have a result here that we can obtain in constant time, and we might have a carry. And now we add these three integers together, we get a result here, and have a carry, etc. So each time we do an elementary operation, this takes constant time. So what's the running time to add two integers? Sort of n digits.
Is it not just
This
all
takes
of
linear
them?
time. Linear n time. Quadratic? No. Logarithmic? No, of course it's linear, right? Because to handle every place here in our every digit of our two numbers takes constant time, so you can do all of this in linear time in the size of the representation of our integers. So you can think of bits, or you can think of base 10. It doesn't make a big difference because, well, base 10 numbers can still be represented by a constant number of bits. Okay. So if we have two n-bit numbers, they can be added in order n time. Can we do this faster? I guess the argument is no, because we have to at least read the numbers that we add together. So we can't hope for anything faster than this. Okay. Now what's the natural algorithm to multiply two integers? Well, I guess you all know this algorithm that you learned in primary school, where, well, you multiply this digit with the first number, and then this digit with the first number, etc. And this will be consisting of order n squared elementary operations. So first some multiplications, and then how many additions? Also order n squared additions. Okay. And doing all of this now gives us a result of length 2n. So the resulting integer has length 2n. So how do we prove that this is optimal? We have two n-digit integers. We have an algorithm with running time n squared. Showing that this is optimal is not obvious, right? Because, well, we can't use the previous reasoning that says, well, we have to at least reach the integers that we handle, but they have size n. We cannot reason that, well, the resulting integer that we output needs to have size at least n squared, because, well, it has actually size only 2 times n. So the size of the output is also linear. So that actually led. Okay, so nobody knows how to do this in linear time. There's an obvious question: can we now do faster than quadratic time or not? There doesn't seem an obvious lower bound. This is the divide and conquer lecture, so maybe you can give it a try. So what are we doing now? We take our two input numbers and split its digits into two. So this is the integer a, and so this whole thing. And now it has n digits, and we split it into two. So we just say, okay, take the most significant digits, that's a1, and the other one, it's a0. Right? And the whole number is now basically a1 shifted by n divided by 2 positions. And shifting by n divided by 2 positions is the same as multiplying by 2 to the power n. And then we express b in the same way. So basically we cut a and b into halves, and then maybe this can help us to multiply these two things faster. Okay, so we're basically going to look at the least significant digits of our result. So remember that the resulting integer has size at most 2n, right? So the size is at most 2n. And I guess we can consider these 4 parts. So for the least significant digits, they're obtained by multiplying a0 by b0. So actually, these things will overlap. But okay, so a0 times b0 is somewhere in here. The most significant digits are on the very left. So a1 times b1 will be over here. And then a1 times b0 plus b1 times a0 will somehow contribute to the middle. Okay, so what have we done now? We have taken our multiplication of two n-bit integers and turned it into 4 multiplications. And each of them, so 4 multiplications on integers of size half of n. Okay, so we have our n-bit integer. We created 4 multiplications. But this is a problem on 2 n-bit integers. We turned it into 4 problems on n half-sized integers. So continuing in the same way, we then at the next level get integers of size n divided by 4, and we have, well, 4 times as many operations as in the previous level. Okay, so now we can use our master theorem. So that's the 4 multiplications we need to perform. This is how we obtain the results. So we compute those 4 multiplications. The W, so that's the most significant ones, they're shifted by n bits. The other 2s are added up and then shifted by n half bits. And x is not shifted at all. That's for the least significant bits. Okay, so 4 operations with on n half digits, and I guess a linear overhead to shift at that. So this is our recurrence now. So we can use the master theorem, figure out the critical exponent, which is log base b of a. So in this case, it will be log base 2 of 4. So that's 2. This is linear, so it's it goes much slower than n squared. So we can say that f of n is order n to the power 2 minus epsilon for some epsilon between 0 and 1. And which means that we find ourselves in case 1. And in case 1, that's the case where the running time is dominated by the size of the recursion tree. And the master theorem tells us that the running time is big theta of n squared. Which means that, well, so we started off from a very simple algorithm with running time n squared, used our fancy divide and conquer mechanism, and ended up with a running time of n squared. So we have made no progress at all. Okay. So, but still the question remains, is there a smarter way to do this? Actually, there is. But back in the 50s, Kolmogorov, a famous mathematician, conjectured that actually you can't do it faster than order n squared. And so he actually started like a seminar series where, well, he met with some of his colleagues and students, and so he organized this weekly series of events where, well, the main problem that they wanted to focus on was to show that order n squared is the fastest you can do, and there's no faster algorithm than this. So remarkably, within a week of the first seminar, a 20-year-old student came up with a faster algorithm. So somebody like our audience here showed that actually you can find a faster algorithm to multiply 2 n-digit integers. So this was presented at in the next week of the seminar, and then the seminar was cancelled. Okay, so what's the trick that Karatsuba did? Well, it's based on the same idea. So we try to do divide and conquer. But now we do a slight rearrangement. Okay, so what's going on here? So we can see that, well, this is the same as what we had before. This is also the same as what we had before. But now, instead of performing these 2 multiplications, we're trying to reuse things that we have already done. So actually, we have already computed A0 times B0 over here. We have already computed A1, B1 over here. And now we're actually multiplying these 2 things that are larger, and then subtracting A1, B1 and A0, B0. So let's try and figure out, so what is this
So
expression?
branches
A1 plus A0
3 instead of
times
4 of
B1 plus
3.
B0. So this is equal to A1, B1 plus A1, B0. Plus A0, B1 plus A0, B0. Okay. And what is it that we actually need? Well, we need A1, B0, so this thing, plus A0, B1. Our multiplication now has over-added stuff. And basically what we have added too much is exactly A1, B1 that we can subtract, and A0, B0 that we can also subtract now. And these are 2 things that we have already multiplied. Okay, so in total, instead of 4 multiplications of big integers, we only need 3 multiplications of, well, big integers of size n-half. Because, well, these integers still have size roughly n-half. Right? We add 2 n-half size integers maybe there's a carry going on and the size increases by 1, but that's negligible. Okay. The important thing is that we saved one multiplication at each round. Okay. Now the algorithm is the following. So we want to multiply two integers a and b. If they have size 1, if they have just one digit, it's easy to multiply them in constant times. Otherwise, well, we break our integers into 2, as before. And now we only need to evaluate 3 multiplications. a0 times b0, a1 times b1, and a1 plus a0. We have to add them first, but adding is fast. Adding is linear time. Times b1 plus b0. Okay, and now we need to multiply n half bit integers, or n half plus 1 bit integers. And then, well, finally, what is our final multiplied integer? That's the most significant digits times 2 to the power n. Plus, this is not a real multiplication, right? Because it's just shifting our bits to the left, which can be done in linear time. So it's although it's written as a multiplication, it's just a shift. And then for the second part, we have, well, the big multiplication, and then we subtract these two, shifted by n half positions, and then in the end, just x, which is the least significant digits. Okay. Yeah, so it's important to note that, well, these multiplications can be done fast because it's just shifting the bits to the left, or padding these numbers with some zeros at the end. Okay, so now we can analyze this algorithm. So we really only care about the number of multiplications because adding is fast. So we create, so we have our problem of multiplying two n-bit integers. We turn it into 3 multiplications of integers on n half bits. And then, well, the shifts and additions all take just linear time, so I have to plus c times n. Okay. So log base b of a is now log base 2 of 3. That's our critical exponent, which is roughly 1.58. And we are again in the first case of the master theorem, because n to the power 1.58 is much larger than f of n. Right? So our critical polynomial is, so we have the case that the so if we compare the critical polynomial n to the power log 2 of 3 against this f of n, we see that, well, this is much larger than this one asymptotically, so the running time is dominated actually by the size of the recursion tree. Okay, so this means that the master theorem now tells us that the running time of Karatsuba's algorithm is big theta of n to the power 1.58, etc. Okay, and so this is smaller than n squared, and this disproves Kolmogorov's conjecture and gives a faster algorithm for multiplying two integers. Instead of splitting our integers into 2 pieces, we can go further and instead split them into more pieces. This will improve the running time, and you can obtain faster running times like this. You can obtain a running time of basically order n to the power 1 plus epsilon for any positive epsilon. But the constant factors involved in the running time are quite large because, well, they actually depend on the number of pieces in an exponential way. So for a large number of pieces, this is not very practical. And these constant, at some point, they start to matter when they become larger and larger. The fastest known algorithm for multiplying two integers even gets rid of this plus epsilon here and replaces it by log n in the base. So there exists an order n log n algorithm by David Harvey, whose office is somewhere in that direction. So he's at the NSW in the math department, and Joris van der Heuvel. Okay, so that's it for multiplying two integers. We can now look at our next example, which is about quicksort and also something called quick select. So of course you know already what quicksort means. And so in this example, we'll be thinking about how can we guarantee actually that in quicksort we do get a nice running time. So ideally, we want to say that, well, if you choose your pivot intelligently, then you can get running time order n log n when using the quicksort algorithm. So we'll see how this can be done. One subproblem is, well, so what happens in quicksort? So we have our array of, let's say, integers. We choose a pivot, and then we'll put all the integers that are smaller than the pivot to the left of the array, then the pivot, then everything that's bigger than the pivot. So the bad cases are, of course, when this pivot is very far to the left or very far to the right. Ideally, we want it bang in the middle, so we want the pivot to be the median of this array. So quick select is an algorithm that we can use to find the kth smallest value in the array. In particular, it helps us to find the median as well. So we'll do a 10-minute break, and then we'll go into quicksort and quick select. Okay, see you in 10 minutes.
I actually don't know what to do here. That's not good. Oh, frick. It's meant to go that way. Whatever. Oh, frick. What can I do here to save myself? Could do that. What to do here? Something like that. Oh, frick.
Okay, let's continue. So in quicksort we have our n integers. We want to select a pivot that is somehow towards the middle of this this array in order to sort it. So the problem is to sort our array A. And yeah, so some simplifying assumption is that all the integers are distinct. Okay, so one simple way we can choose the pivot is just to take the first element. Let's say the first element acts as our pivot, and then what the algorithm does is, well, put everything that's smaller than the pivot to the left, then the pivot, and then everything that's larger than the pivot to the right. Okay, this is of course not very good if the array is already sorted, because that's actually the worst case, right? Because then, well, you end up with nothing to the left of the pivot, and then the pivot, and then everything else to the right. Okay, so at each recursion step, the running time is big theta of n. And ideally, the pivot breaks our array into two halves, into two arrays of size about n half. So in this case, in this best scenario, and if this best scenario keeps happening well, at every step of our recursion tree, then what we get is a running time of big theta of n log n. Because then in that case, the running time would be 2 times 2 divided by 2 times t of n half plus big theta of n. So the critical polynomial is n to the power log base 2 of 2, which is just n. And well, this is the same as n. And then we have this logarithmic factor here. But in the worst case, our pivot doesn't break up the array nicely, and everything is either completely to the left or completely to the right of the pivot. So in that case, we actually get a recursion tree that has depth n, and we have a running time of n at each level of the recursion tree. So in total, the running time is order n squared, or big theta of n squared. Okay. We should note that the worst case is very rare. So even a split of 9/10 of the integers being to the left and 1/10 to the right would be nice, because this will enable us to upper bound the running time in a nice way. It will give us a running time of big theta of n log n. So the pivot that we choose doesn't need to be bang in the middle, but situations that we want to avoid is that the sublinear number of elements are before the pivot or after the pivot. So if it's a linear fraction, that's fine. Okay, and then in the Corman-Lisenson-Stein book, we can, there's a proof that the average case complexity is big theta of n log n. But we actually want to have statements about the worst case complexity. So the question is, well, can we have a pivot selection strategy which, no matter what our array is, it always gives us a running time of order n log n? The question is, can this be done or not? Well, you could, instead of taking the first element as your pivot, you could choose some element at random. You could take the median of the first, last, and middle number in your array. Well, let's see. So if you choose an element at random, in the worst case, it still gives you either the smallest or largest integer in the array. So if we analyze the worst case, basically choosing something at random is not, it doesn't really help us. If we take the median of the first, last, and middle element, so we have these 3 integers, the median of them, well, we're guaranteed that there exists at least one element that's smaller than our pivot, and there exists at least one element that's larger than our pivot. So it helps a little bit, but the guarantees that we get are not very good, because, well, we still only have a constant number of elements that are guaranteed to be to the left of the pivot, and that are guaranteed to be to the right of the pivot. So this still gives us a worst case complexity of big theta of n squared. So what we really need to do is find some element of the array where a linear fraction of the elements are guaranteed to be on the left, and the linear fraction of the elements are guaranteed to be on the right. So one thing to note is that if we look at the master theorem, then, well, actually, since partitioning the array into twos already takes linear time, it doesn't hurt us if our pivot selection strategy also takes linear time. It doesn't increase our function f of n, except maybe by a constant factor. So the most time that we want to use is order n to actually find a nice pivot. Okay. So now we are looking at a related problem, which is, so we have an array A of n distinct integers, or n elements, and they can be compared to each other. They don't have to be integers, but you can think of integers as a natural case. So k is some number between 1 and n. And this selection problem says, well, find the case smallest entry of A. So if we can solve the selection problem, then we can also find the median of our array, right? Because the median is just the selection problem where k is equal to n half, rounded up or down. Okay. So our first attempt to find the case smallest entry would be to sort our array, and then we return the element at the case position. But the problem is that this requires us to sort, which takes running time order n log n. So this is too slow because actually we want to do it in time order n only. Okay, but well, the selection problem is easier than sorting because, well, sorting actually solves the selection problem for every possible k at the same time. Right? We only need to solve the selection problem now for one value of k. The question is, can we do better than sorting? Okay, let's take another attempt and use our divide and conquer strategy. So we could take some element as pivot, maybe it's the first element of the array, and then, well, all the elements that are smaller than our pivot go to the left of A. Then we have our pivot, and then everything that's larger than the pivot. It's basically the same as quicksort, more or less. Now, so let's assume that the pivot will occur at index j of our array A. Okay, then now the k smallest element, we need to decide where is it. So it's either exactly where the pivot is, or it's to the left, or it's to the right. So if our pivot happens to be the k's smallest element, then we just return it. If our pivot is at a place larger than k, then, well, the k smallest element will be to the left of the pivot. So we only need to look at the left part of the array. And otherwise, we will find it in the right part of the array. And so basically, we can already, in that case, we can discard the j first elements of the array. And now, instead of finding the k smallest element in the resulting array, we will find the k minus j's smallest element of that array. Right? So we have our pivot x, well, we just chose it as the first element of the array, and then it moves into some position j. All the smaller elements are to the left, or the larger elements are to the right. And now the k's smallest element, let's say k is this value. So k is to the left of j. If the k is smaller than j, we'll find it in the left part of the array. We only have to focus on that.
Huh?
Okay. Of course, the best case is when the pivot that we selected is already the median. So it's, in that case, so our problem halves in size at each recursion step. So this recurrence here is now independent of k. So no matter what k is, we can always. So if our pivot happens to be the median, our running time can be expressed in this way. Okay, in that case, we do have a linear running time. But if our pivot is something very small or very large compared to the other elements of the array, then we still have a running time of theta of n squared. And again, if we actually manage to find a constant fraction of the elements to the left of the pivot and a constant fraction to the right of the pivot, then we would achieve a linear running time. The average complexity is again handled in this textbook, but we will actually look at the worst case complexity. Okay. So finding the median is a special case, of course, of our selection problem. When n is odd, it's clear what the median is. If n is even, it's not that clear.
I can show you an algorithm called quicksort. Hopefully this bit of paper here will be sufficient to do that. Okay, so again, we start with an unsorted list. This time, we partition the list into 2 bits. So rather than just splitting it into 2 bits of equal size, we take one element, which we call the pivot. It doesn't really matter which one you pick. I mean, actually, it does matter a little bit, which I'll get into in a minute. Okay, so we pick one called the pivot. We'll just take the rightmost one. Okay, so we've got 5. So put that there. So every element in this list that is less or than or equal to 5 goes on this side, and every element that's greater than it goes on this side. So 7 goes on the right, 8 goes on the right, 7 goes on the right, 4 goes on the left, 3 goes on the left, 10 goes on the right. So then we do the same again for these 2 sublists we've got. So we take 3 as the pivot for this one, and 4 is greater than it, so it goes on the right. So with this one, we take 10 as the pivot, so everything less goes on the left, so it's actually all the elements. And then we keep breaking these down so we've got either one element or no elements in each list, so we know they're sorted. Okay, so we take 7 as the pivot, 8 goes on the right, and 7 less than or equal goes on the left. So then we join all these lists back together. So we start at the bottom, we take the pivot, everything on the left goes behind it, everything on the right goes on top of it. Okay, so we've got the pivot here, put 4 on top of it. We've got 10 here, everything on the left goes behind it. And then here we've got the pivot, so these go on its left, and these go on its right. Okay, so now we've got one sorted list. Now, you do have to be careful about what you choose as the pivots. Usually what they'll do is you'll either pick the first element or the last element because it's just easier. Ideally, you want to be able to split the list into about 2 even parts, so really you want the pivot to be the middlemost number, but you don't know what that is at the start. So in the average case, it's the same as merge sort. We've got n times log n, and in the best case, it's still n log n. But in the worst case, well, let me show you. Okay, so let's say we've got a list that's already sorted. So I'll just take the cards we had before. If we always choose the pivot from the rightmost element, we've got 10. So 10 is the pivot. So all the elements less than it go on the left. So we've got all the elements basically. Okay, so then we pick 8 as the next pivot. All the elements go on its left. Then we pick 7 as the next, then all the rest go on the left. Then we pick the next 7. And what you see is we end up with cards all the way down here. And then we've got to merge them back together. Okay, and actually that works out in the worst case as n squared. So again, it's the square of the input size. So we've got the worst case of bubble sort is still n squared, and the worst case of merge sort is still n log n. The highest card will definitely have been swapped all the way to the end. So actually, you don't need to check that one anymore. You can move that off and just go.
These third-party cookies allow the advertisers to figure out, have you seen this advert before?
We use the same convention as in textbook, which tells us to actually select the lower median in that case. So the value that's, well, there's no exact middle value, but take the one that's slightly to the left of what would be the middle. Okay. Well, finding the median, of course, well, you already know it can be done in n log n time, just by sorting. The average running time will be order n, but we actually want to find a worst case linear running time. And we'll do this again using divide and conquer. And the first thing that we are doing now is to take our array and chop it into blocks of size 3. So we'll have n third blocks of 3 consecutive numbers. We take our array, and now we'll take the first 3 values, chop our array here, next 3, chop it here, etc. Now, from each of these blocks of size 3, we will discard the smallest and the largest number. We keep only the median of this block. So now we have n third numbers, and we will try to find the median of those. Is this algorithm actually correct? I think we could have actually discarded the actual median of our array by doing this, right? Because we are not guaranteed that the median of the whole array is the median of one of these blocks of size 3. So in this example, we have 3 blocks of size 3. What is the median of this whole array? 5. Let's see, we have 1, 2, 3, 4 numbers that are smaller than 5. The other ones are larger. Yeah, so 5 is the median. But, well, our algorithm would have discarded the 5, and it would actually have returned this value as the median of medians. Okay? So our algorithm is incorrect. But the approach is still helpful, because we can determine that, well, some numbers are definitely not the median. Okay, I think there's a picture here. So let's say we have our array. Now we have written it, like, well, this is the first entry of the array, this is the second, this is the third, fourth, fifth, sixth, seventh, eighth, ninth, etc. So we have already visualized it in blocks of size 3. Now, well, we wanted to focus just on the second row, right? Just on the medians of these blocks. So actually, let's rearrange our array and sort them according to those values. And our algorithm would have found this, this value here. Okay, but there's a couple of things that we can observe. Namely, so this is the median of medians, in yellow, no? So we can observe that, well, the number that we got here, so the 60, is larger than all of those numbers that are in blue, no? And it's larger than also those numbers that are in the same block as those medians that are smaller than the 60 and are smaller than the median. Okay. We can also observe that the 60 that we got is larger than all of those in magenta and those in magenta as well. Okay, so the number that we get might not be the median of the whole array, but it is somehow towards the middle because how many numbers are here? So here we have n-third of those blocks, right? And from half of them, roughly. So here we have roughly n divided by 6 blocks of 3 numbers. In each of them, we could find 2 numbers that are smaller than the 60. So the 60 that we found, the median of medians, is larger than 1/3 of the numbers. And it's also smaller than another 1/3 of the numbers. Okay, so the median of medians might not be the actual median, but it's somewhere in the middle third. And actually for quicksort, this is already enough. So if we find a number that's in the middle third of our array, then we're happy. Because, well, we guarantee that, well, the pivot that we select for this pivot, at least the third of numbers will be to the left of the pivot, and at least the third to the right. So even though we might not divide our array into 2 halves, we still divide it into, well, in the worst case, 1/3 and 2/3. Okay, but you can actually try to find the actual median as well. So we have, so the median of medians is greater than roughly n-third array elements and less than also roughly n-third array elements. So it's in the middle third of the array. And we know that, well, both quick select and quick sort have good performance as long as a constant fraction of the elements will be to the left of the pivot and at least a constant fraction will be to the right of the pivot. So we can use our median of medians. Okay. So our second attempt is now to divide our array into n-third blocks of 3 consecutive numbers, find the median of each block. Now we do a recursion. Well, in the recursive call, we find the median of these medians. So now we have n-third numbers, and we want to find the median of those recursively. Once we find it, we'll designate it as the pivot. Now put all the values smaller than the pivot to the left, followed by the pivot, followed by all the values larger than x. And let's assume that the pivot goes into position j. And now, well, to solve quick select, we again have these 3 cases. Either k is equal to j, in which case we just return the pivot, or k is smaller than k, in which case we look at the left side of the array, or k is larger than j, in which case we look into the right side of the array. Okay, so let's calculate the running time. Well, forming our blocks takes big set of n time. Each block has only 3 items, so sorting these 3 items takes constant time. And then we can also pick the median of a block of size 3 in constant time. Then we recurse on the medians of the blocks. So we have n-third many medians of the blocks. And so our recursive call takes time t of n-thirds. And then we need to go through the array again to put the pivot in the middle, everything that's smaller to the left, everything that's larger to the right. So this is also linear time. And then, well, what we said is we're guaranteed that the median of medians is in the middle third of the resulting array, right? So if we take our array, and so in the worst case, the median will be exactly at the point at this 1/3. Is it more or less? Let's assume that this is more or less at the 1/3 mark. So when we now look at finding position k, then so maybe we have to look at this big part of the array, which still has size roughly 2/3. Okay. So the running time that we get is t of n-thirds plus t of 2 n-thirds plus big set of n. So let's use the master theorem. Actually, can you use the master theorem? So usually we had recurrences of the form A times T of n divided by B plus f of n. Right? But now we have these two things, right? So we can't directly use the master theorem, but we can still reason about the time that's needed, right? Because, well, what's going on here? So we have an array of size n, and we need a big set of n time over here. And then we chop it into 1/3 and 2/3. And the running time that we need at this level is also big theta of n-thirds plus 2 n-thirds. But we still need to go through both parts of these chopped up away. So the running time is still big theta of n. And so this continues at the next level. And at each level, the running time will be big theta of n. The depth is logarithmic in n. So we still need running time big theta of n again. We wanted to get linear running time, right?
Isn't it
So
impossible to get
we can
linear
have made no
runtime?
progress. So why is this? Because, well, the computation time at each level is, it takes n steps each time, or it's t times n steps. So that's the big issue. If we could somehow, remember the case 3 of the master theorem, case 3 said that, well, this case can be applied if, well, the computation, so here we had, so basically it said that the computation on the next level should be smaller by a fraction that's smaller than 1. So the condition said that, well, here the computation time needs to be at most c times n for some c that's smaller than 1. And in that case, so that was also the case where we could argue that actually the running time, the total running time, is dominated by whatever running time is needed to handle the first level. And the first level needs linear running time. So we're going to try to make some progress so that at the second level, actually, we need less than n steps. There's one arbitrary choice that we made, which is we chose blocks of size 3. The suggestion here that maybe we should increase the block size to 5, maybe to square root of n. Let's try with 5. Okay. So we have n-fifths blocks. Is there a picture for this? Yep. This is not sorted. Let's sort them. Yep. So now we have these blocks of size 5 now, right? So the median of medians of these blocks will be over here. We have, how many columns are here? We have n divided by 10 such columns.
Still a third.
That have medians smaller than the median of medians. And we know that, well, in each of these blocks, 3 numbers are smaller than the median of medians. Okay. Maybe we haven't made no progress. So previously we had 1/3 of the values that were smaller than median of medians. Now we have 3/10 of the values. Okay. So let's see what happens. So all of these numbers are smaller than the median of medians. All of the magenta numbers are larger than the median of medians. Okay. So our median of medians is greater than 3 of the 5 elements in n over 10 of the blocks, and less than 3 of the 5 elements in another n over 10 of the blocks. Okay, so that's why, well, it's not among the first 30%. Our median of medians is not among the first 30% of the array elements, and it's not among the last 30% either. It seems that this is worse than what we had before.
Oh.
But there's a big difference, namely that we now recurse not on n-third of the values, but only on n-fifth of the values. So maybe this still helps us. Okay, so our median of medians of the blocks of size 5 is definitely in the middle, well, with 3/10 to the left for sure, and 3/10 to the right. So there's 4/10 left, so it must be in the middle 4/10, which is the middle 2/5. Okay, so our new algorithm is now, instead of dividing into blocks of size 3, we take blocks of size 5. The rest is the same. Everything else is the same. Okay, so what's the running time this time? Again, we have linear running time to chop up our array into blocks of size 5. In each block, we can still find the median in constant time. Then we recursed on the medians of the blocks. Now the important thing is that the running time is now t of n divided by 5. And partitioning takes a big set of n time. And now, well, since the median of medians is between the third and seventh deciles, so this last step here, this last step looks at arrays of sizes at most 7n over 10, right? Because we're guaranteed that the our pivot that we selected is somewhere in the middle 2/5, which means that we have discarded either the first 3/10, so we're left with a problem size 7n over 10, and we have also discarded the last 3/10. So we have discarded either the first 3/10 or at least the last 3/10. Okay. So the last step now takes time, t of 7n over 10. Okay, so we can again look at our recurrence. Now, instead of n thirds and 2n5ths, we have t of n equals t of n divided by 5 plus t of 7n divided by 10 plus etc. Surprisingly, this actually gives us a linear running time. And the main thing the main observation that we need is that so at the next level of recursion, the running time will be linear. Right? So the next level of recursion will take some constant type times n divided by 5 times, plus some constant type times 7n over 10 times. And because, well, 1/5 plus 7/10 is less than 1, previously we had the 1/3 and 2/3 that added up to 1. This is actually enough to make the running time at the next level smaller, and then the running time at the next level again smaller and smaller. So most of the running time will be spent at the top level. And at the next level, we need a time that's n/5 plus 7n/10. So
Bro,
the running
what
time
the
decreases
frick?
by a constant factor that's smaller than 1. So it decreases so it becomes 9/10 times n. And it keeps decreasing that way. Right? Okay. So we have the linear time that we need at each recursive call. But we group them together, right? So we look at the whole time that's needed for a whole level of the recursion tree each time. So at the case level of the recursion tree, the number of elements or the subarrays that need to be considered have this many elements. So the number of elements multiplies by some number that's smaller than 1, 9/10 at each level. And so now the question is, so what is the sum of these numbers? So it's n plus 9/10 times n plus 9 squared, 10 squared times n, etc. So it's the sum from I ranging from 0 to something of, let's see, 9, 10 to the power I times n. We can take the n out of the sum. And now we need to figure out what is the sum. So that's actually a geometric series. And we can upper bound it by 10 actually. So because these numbers become smaller and smaller. We start off with 9 divided by 10, then 81 divided by 100, then 729 divided by 1000, etc. So we add up these numbers, and this whole sum, even when going to infinity, it will add up to almost 10. Okay. So which means that actually we now have a linear running time for our selection problem. And in addition to the selection problem, we can now solve quicksort, right? We can now, to do quicksort, instead of finding or choosing an arbitrary pivot, we'll take the median of the array as a pivot. Well, I guess there's a choice. You could either compute a whole median, which takes linear time, or you could take the median of medians, which is faster by a constant factor, but is not necessarily bang in the middle. But in any case, you will get a worst case n log n running time for quicksort. So if we do select a median for quicksort, by selecting the median, we saw how to do it in order and time. And now we're guaranteed that the pivot is actually bang in the middle, and we need to solve two subproblems of size n divided by q. So then we can actually use the master theorem to upper bound the running time of this variant of quicksort in time big O theta and log n. So is this better than the original quicksort? So we have improved the worst case running time by a smart pivot selection strategy. But you could sort of see that, well, there's large constant factors involved in selecting this median, so that's why it's not completely clear, right? So the worst case improves, but probably the average case has probably worsened because there's significant overhead in finding median. So these hidden constant factors, actually they might be important in practice. Actually, in many practical applications, the guaranteed slower running time by finding the median makes the strategy quite slow, and maybe using a random pivot has better performance. Okay, that's it already for the lecture. Do we have any questions about quicksort or quick select? Okay, so then I'll just leave you with a puzzle for the end. So we have 5 pirates that need to split 100 bars of gold. They all line up and proceed as follows. So there's an ordering of the pirates, and this ordering is known to everybody. The first pirate in the line proposes a way to split up the gold. For example, the first pirate might suggest everybody gets 20 bars. So afterwards, all the pirates, including the one who proposed, vote on whether to accept the proposal or not. If the proposal is rejected, the pirate who made the proposal is killed. And then the next pirate in line then makes his proposal, and the remaining 4 pirates vote again. If the vote is tied, the proposing pirate is still killed. Only a strict majority can accept the proposal. And so this continues until either a proposal is accepted or there's only 1 pirate left. I guess if there's only 1 pirate left, the pirate will vote to accept the proposal. And we assume that every pirate has the same priorities in the following order. 1 is not being killed. Second one is getting as much gold as possible. And the third one, well, seeing other pirates get killed. This might also increase their share of the gold, right? Or it could be just for fun. So the question is, what proposal should the first pirate make? Well, you could ask, wouldn't the other pirates kill the first pirate anyway because, well, they might increase their own share? But then I guess it becomes riskier that they are killed themselves, right? So some kind of a balancing act that they need to think about. So there's a hint here. Assume first that there are only 2 pirates and see what happens. Then assume that there are 3 pirates, etc. So it's kind of go backwards from the end, using something called backwards induction. And then further we assume that there are 4 pirates, and they have figured out what happens if there are only 3 pirates, and try to figure out what they would do. And then you look at the 5 pirate case, and then you assume that, well, the 4 pirates that will be left in the end make optimal decisions, and then see what the first pirate actually did. Okay, that's it. Katie will take over next week, and I will see you in week 10. Thank you.
Just week 10?